Alright, welcome to lesson 9. Lesson 9 will be a short lesson. It will have two pieces, an intuition piece and a mathematical piece. Mathematical piece will be optional, so feel free to skip it. We're gonna talk about underfitting and overfitting. It is a short lesson, lesson 9, but extremely important. Because as a data scientist, you will deal with underfitting and overfitting all the time. Yeah, you're gonna mainly deal with overfitting. It's very easy to overfit your data. Underfitting is sometimes called bias, whereas overfitting is called variance. And there is a trade-off between these two. Yeah? That's why there is a trade-off between generalization and approximation. Or a simple model versus a complex model. A complex model will fit the training data more closely, but it will generalize less well on new data. Yeah? So that's the trade-off we have to deal with all the time. Let's take a look at a few examples. Yeah? Here, for example, I have the blue line is my training data, and what I'm going to do is I'm going to draw a model This is my model h of d. Now, it's just a straight line at y equal to 0. You can easily see that the red line does not represent the blue line very well. So this is definitely a case of bias. Means you got the wrong HD. Yeah? Here the same thing. Remember we looked at a classification problem when we dealt with the sigmoid function. And we have data here in the lower left corner where y is 0. And in the upper right corner we have y is 1, also a bunch of data. So we could connect this data with a line. This line could be h of d, our model, hypothesis, based on the data. But you can immediately see that it does not represent the data well. And remember, that's why we came up with this type of function, which we call the sigmoid function, yeah? Which we use for classification. So this is definitely also bias. Yeah? Let's take a look at this example. Assume that we want to isolate the crosses. Yeah? We can start here, like this. Like this, and then gotta turn around here, and then take these. So look at what extent I had to go in order to isolate the crosses and the circles. So this is definitely, this is your decision boundary, and this is definitely a variance issue. You overfit. Remember that we dealt with predicting the housing price, where we had the size of the house versus the price. And we made, we modeled it through a straight line. Y predict equals Wx plus B. So y predict is the same as your HD, your hypothesis with respect to the data. And the black line is actually the best line that connects these 6 points. Yeah? And we had a way, the mean squared error function, where you would basically minimize the distance between these points and the line. Yeah? And then you add all these lines up, you divide by the number of training samples, and this will give you your error. Yeah? But if we would have chosen a model that would really go through all these points here, then we again would overfit. because the training data, the red line, connects the training data 100% without any error. So you say, wow, my training error is 0, I have the perfect classifier. But when you will apply your model on new data, you will see your error will be high. Yeah? So we need to constantly monitor that our model is not too complex. Yeah? So we need to take care of overfitting. Underfitting is also an issue, but happens a bit less. As humans, we have this desire to, make sure everything fits, and that's why overfitting is more an issue than underfitting. Okay, let me give you some other intuition on variance and bias. Low bias means that your model fits the data well. You have a simple model and you're spot on. Yeah? Spot on meaning you're right in the middle here. Low variance meaning you stay close to the middle. Yeah? Low bias means again you're centered in the middle, but your crosses are spread a little bit more extended. The red crosses are extended a bit more. High bias means you're not on target, you're off target. But variance is low, so you're off target, but your crosses are close to each other. High bias, here you're still off target, but there's a bit of a higher spread with respect to the crosses. Yeah? So this is the way you have to see it. Okay, now how do we calculate the expected error? Well, we draw a data set from a distribution P that we don't know. Yeah? Then we train the model and we come up with an HD, yeah, which is our Y predict. And then we take a test point XY and we calculate the expected error. Yeah? Sigma squared here is just a noise. This is just a noise of the data. And you cannot take this away. Yeah? This one is the variance. This is the range of HDs. The range of HDs could be, one HD could be a straight line, another HD could be a polynomial, another HD could be a sigmoid. There's a range of all the models you could apply. Remember that in this case here, it's us that determined that we want it to be linear. So we have selected the linear model here. Yeah? But there could be more models. So this gives you the range of all the models. And this one by square HD gives you how far is your HD from what you expect it to be. Yeah? There is an expected value for your model. Well, how far is your model from that expected value? That's given by the bias term. So the expected error has a noise factor, a variance factor, and a bias factor. So now we're going to derive this formula. It's going to be a bit technical. Feel free to skip